exam, you shouldn't feel worried about the exam.
That's what he says.
Well, it's one of the few exams that you can just turn in something blank and there's no repercussions. So that's why you shouldn't wait. Yeah, it won't be, yeah. So treat it as a fun exercise to see if, took something away from this. But more on that later. Right now, André is going to give us his final lecture on effective field theories. So I hope André finally gets to talk about his one loop example.
Oh, we're going to start with one loop.
Oh, great. Okay. Thank you. Take it away, André.
Okay. So, welcome. Good morning. I've been saying I'm trying to give you a recipe, an algorithm, which I am. But today I'm also going to encourage you about certain ways to think about field theory. So it won't be just a complete recipe. Okay, one loop graphs. Let's begin where we left off. We're going to start with the quark mass operator, because that's the easier one to deal with. And just recall, this is the operator. And what we're interested in are terms which have 4 pion fields, because we want to draw a self-energy correction that's going to look like this. Oh, not draw. We can draw that. We want to work it out. And so this is going to contain the following. I'm going to focus on the charged pion mass. So I'm only going to write the last term to correct a mistake I made in the sign when I wrote it yesterday of the pi not to the 4th term, but we can ignore that. So for the charged pion mass, or either charged pion, we can see only these 2 operators are going to contribute to the self-energy, because pi 0 can't couple to the pi plus. The annihilation and creation operators in the pi 0 field won't create or annihilate a pi plus. So, Wick contractions. So just to repeat, so this is the first operator. When we're contracting the fields, I have a choice of whether to use this field or this field, the annihilation operator in them, in order to contract with the creation operator from the pi plus here, right? So this pi plus is really pi plus dagger vacuum. And so I need an annihilation operator from one of these 2 fields. And again, there's a choice of 2. I can pick this one or this one. Not only can I have to pick both choices. So once I make one, I have one choice, and I have 2 things I could have done. Same over here. There's 2 things I could have done. And once I've made these choices, there's only one way these can tie together. So this gets me a factor of 4. With this one, there's only a factor of 1. This can go to this one, this goes to that one. That's all that we're allowed to do, and then the pi zeros contract together. Excuse me. It's not an easy way to mute. I'll get some water, yeah. I'll get some water. But, so, what does that mean for our self-energy? Recall, as we worked out the other day, when I consider a graph, this is the amplitude, which is also minus a self-energy correction. And so this particular self-energy correction is going to be I get an I, because remember I have I times the interacting Lagrangian. 2b, remember m hat is the average up and down quark mass. And then I'll get a term, an integral that depends on the pi 0. And then, because of this factor of 4 times an integral that depends on the pi plus. Now, what is this integral? I'll just write it down in dimensional regularization. And recall, this bar means I have the 2 pi sucked in there. Okay, why are we going to use dimensional regularization? And everybody, I think, calls it oftentimes dim reg for short because it's much quicker to write. Number one, it's automatically, we'll see this in detail. It automatically subtracts power divergences. Do you guys know what power divergences are? Everybody knows what power divergences are? No? Okay. A power divergence is if I look at the mass scaling of this integral, just being a little fast, I have, let's just think about 4 dimensions for a sec, not the d. So I set d to 4, so mu goes away, this becomes a d4k. The mass dimension of d4k is 4. The mass dimension of the propagator is -2. So that means if I don't do anything special, I just were to put a momentum cutoff in the integral, it would go like that cutoff lambda squared. So that's a power divergence. Anything that's a positive power of the high momentum scale, or like if you did polyvolars, you would also get, if you set the polyvolar's mass to lambda, you would also get a lambda squared. That's called a power divergence. Those are things that go to infinity as we take our cutoff to infinity. And those are bad in a few, I mean, strictly speaking, there's nothing wrong with it. But if you put in a regulator that has a power divergence and you're interested in low energy physics, you have to add a counter term that is equally big, and so it subtracts against it to uncover the very small physics you're interested in. So it's unnatural in that sense, and this is why we don't like power divergences. So dimensional regularization automatically removes all power divergences. It makes things easy. And 2, another important feature is it respects chiral symmetry, which is related to the power divergence. And because we're studying chiral perturbation theory, from which chiral symmetry is a very foundational point, it would be nice to use a regulator that respects chiral symmetry. Otherwise, we'll have to, in the same way, fine-tune our chiral symmetry back into the calculation. Okay, now, before we think about evaluating this integral, there's some things you should do right away. First, understand what you expect the integral to behave like. So if we remove power divergences, how can this integral be, how can it scale after I do the integral? Like what am I trying to get at? This, k is a dummy variable, so in the end of the day, the integral can't depend on k, right? After I integrate over k. There's only one other scale in the problem, which is the mass. So this integral has to scale like m squared. There's no other choice. And that you can just look at a diagram right away and say, this has to go like m squared. And so that's how you start building up a power counting idea. Like, oh, okay, this one goes like m squared. And the other important thing to note, these integrals always come with powers of 4 pi squared in the denominator. And then, looking back at our Lagrangian, you can see m squared over 4 pi squared, and there's this 1 over f squared. That's my small expansion parameter of the theory. So I can see that this integral is going to be suppressed by 1 power of the small parameter, or my perturbative parameter. Because I have 2bm hat, which is the pi mass at leading order, and then I multiply that by m pi squared over 4 pi squared with an f squared. So I can immediately see this is suppressed in the power counting. So that's the number one thing, one of the most important things to take away is to be able to look at an integral and quickly understand, or a diagram, really, look at a diagram and quickly understand what order you expected it to appear, because then you can decide if you have to work it out or you can ignore it. And this is how you build up the power counting for doing the calculation. So the easy part is figuring this out. The hard part is figuring out the factors of I and 2 and minus signs. That's where you have to maybe go into a dark room, as we say, and work it out yourself, or argue with your best friend at the board for 2 hours, whatever it is. Okay. So we already called this small parameter, I'll just write it again, epsilon pi over 4 pi f. And usually I like to work in what's called on-shell master normalization, so I often will write this as f pi because I think of this as the physical pi and decay constant, which will require some algebraic manipulations later, but that's okay. And so this integral is suppressed by what I call epsilon pi squared. So how big is this epsilon pi? M pi, let's say take the pi 0 as a definition for the pi mass. It's 135 MeV. F pi is 92 MeV. So 4 pi F pi. It's like 1150 MeV. So that means, or even my notes have a slightly more precise number. So that means epsilon pi is about 12%. But in chiral perturbation theory, we will find all the corrections scale like epsilon pi squared, not epsilon pi. And so epsilon pi squared, well, this number is 0.014. This is a 1.5% correction. And this is why chiral perturbation theory works so well. The small parameter is a few percent. So if I go to next to leading order, I can anticipate a couple percent correction to leading order. Except for maybe sometimes there will be some combinatoric factors that give an enhancement. But that's the scale you should expect, a few percent. And so then N2LO, you'd expect an even smaller correction, because it would go like epsilon pi to the 4. And in the same way, you can see this is why when you add the strange quark and you have a kaon, it doesn't work nearly as well, because the kaon mass is like almost 500 MeV. All right. So, dim-reg. Let's do this integral in dimensional regularization. So, D, what we're doing in dimensional regularization is slightly modifying the space-time dimensionality. We're giving a small correction to 4 dimensions. And this is just a mathematical trick to understand how to isolate the divergences of the integral. Essentially, it's like some enhanced complex analysis. I'm looking at Andrew to see if he agrees. Okay. And then the other quantities that are going to show up, we have a d over 2, you'll see. So this is just 2 minus epsilon. I just always write these down for myself to remember how to scale everything. I write them down particular to the diagram that we're going to end up with. So here we go. what do we get? We're going to get I from our propagator. We're going to get a minus I from applying the dimensional regularization or doing the integral, 4 pi to the d over 2. So I'm not going to derive this for you because you can go check this out in most quantum field theory books, how to actually get this formula. I'm just going to walk through manipulating it after it's obtained. And then I have 1 over m squared. And then I have finally the mu to the 2 epsilon. Okay, so the i's nicely cancel for me. I get 1 over 4 pi squared. There's going to be a residual 4 pi to the epsilon from here. I'm going to have a mu to the 2 epsilon, m squared to the 1 minus epsilon. Then I have this gamma function. And then you can look up some formula for the gamma function, or you can ask Mathematica or some other thing like your brain to do a Taylor expansion. What do we get? M squared over 4 pi squared. 4 pi to the epsilon. Now I have mu squared over m squared to the epsilon power. And this gamma function is going to be 1 over epsilon minus some constant plus 1 plus some stuff that's scales like order epsilon. So I can ignore it. I can ignore it because when we do dimensional regularization, what we do is we isolate the 1 over epsilon pole. That's the remnant of the divergence. We find all the stuff that's finite and will not vanish as we take epsilon to 0. Because what we want to do is take epsilon to 0 in the end. That's going to remove the regulator. So now I'll walk you through the trick we do. We take this 4 pi to the epsilon, mu squared over m squared to the epsilon, and we rewrite that as the exponential of the log of 4 pi mu squared over m squared to the epsilon power. And then we use the rules of the log to pull the epsilon out front. So it's e to the epsilon log 4 pi mu squared over m squared. And then I say, wait a second, I know epsilon is small, so I can do an expansion. So this is going to be 1 plus epsilon log 4 pi mu squared over m squared. And like I said, what we need to do is we need to keep track of the 1 over epsilon pole and all finite terms that survive. The epsilon goes to 0 limit. So then I take this log and I remultiply, so I have my integral . And so then when we get the 1, obviously you get what you started with. Now the epsilon will cancel against the 1 over epsilon, or they multiply to 1. But then epsilon times all the rest of the stuff will be order epsilon in the end. And so as I take epsilon goes to 0, it all vanishes. So all I have to keep track of is this term times the 1 over epsilon. And hopefully this now starts to look familiar to you from loop integrals you may have done or read about. Okay, so again, as promised, no power divergence. It's gone. DimReg has removed it for us. We only have a 1 over epsilon pole. Now there's some other subtleties you have to be careful with. We'll talk about later. But essentially, this is now a regulated integral. Not renormalized yet, just regulated. Well, yeah, it's regulated. It's finite. And then to renormalize it, what I have to do is I have to subtract the 1 over epsilon term by adding a counter term to the theory that also has the 1 over epsilon pole, but with the opposite sign, so that when I add the sum of my quantum fluctuation plus my new counter term, the sum of these things, the 1 over epsilons, exactly cancel. So this 1 over epsilon shift will be a shift in one of the parameters you have in the theory that has this ultraviolet divergence, in this case, and you're subtracting it away. And when you do that, you're free to take as much of the finite stuff away with it as you want, because this new parameter you have to add to the theory has a coupling that you do not know yet, because this is an effective field theory. And so you're free to arbitrarily suck up as much finite, well, even if you knew the exact theory, you're also free to suck up all the finite stuff you want. But the point is, there's some coupling we don't know, so we might as well take away as much finite stuff as possible to minimize the number of things we have to write down to make it less likely we're going to make a mistake when we're doing the math. So this, we add a counter term to get rid of the 1 over epsilon. And then what I'm going to say is the interesting part of any field theory, in particular effective field theory, are going to be these terms that scale logarithmically in our small parameter. So this, I want to talk a little bit about this. So why? Again, this 1 over epsilon stuff and all the finite things, because I can subtract it with a counter term, this is essentially a short distance physics piece. And in the effective field theory or in quantum field theory, what we're interested in is the long-range dynamics of the theory, not the short-distance physics. The particles that can propagate a long distance and impact other particles around them, that's the interesting physics. This is just short-distance physics. We don't care about it, right? So we subtract it. Now, if you subtract just, so the different subtraction schemes, just to tie it to the literature. There's MS, which is minimal subtraction. This is, here you only remove the 1 over epsilon. Now the cases where you want to use the minimal subtraction scheme are if you're working in a field where everybody else has done that, you're just forced to do it so that you can use the same renormalization group equations they have. But usually what you do, you use MS if you want to do what's called solve for the anomalous dimensions of couplings in your theory to sort of build in some of the higher order corrections. Maybe you don't want to do the full two-loop calculation. You just want to get the important aspects that come out of the two-loop calculation. And the way you can do that is simply by following the 1 over epsilon bits. And so if you just do minimal subtraction, essentially, or in fact, you almost don't do the subtraction. You keep track of the 1 over epsilon terms, and that's how you can track how the operators in your theory will scale as you change their normalization scale. There's MS bar, which is modified minimal subtraction. In MS bar, that's the other common one. It's 1 over epsilon minus gamma plus log 4 pi. You subtract all this stuff. In chiral perturbation theory, there very often is this extra annoying +1. And so in chiral perturbation theory, I call it MS bar bar. I don't know what the actual name is. Then you just subtract everything. Yeah, modified. But again, I don't know if there's an official name. This goes back to Gassler and Leutweiler when they first wrote down the chiral perturbation theory papers. They also were annoyed with the 1, so they subtracted it as well. So again, when we do this, we are regulating the integral. We have not yet renormalized the theory. We're just regulating. Regulating means cut off the UV divergence, and then renormalize means we can't have any actual dependence on this renormalization scale mu. So we have to add operators that have the correct scaling in mu such that the sum, again, so I have a counter term where I'm going to subtract this UV bit, but then, so I can call it a C epsilon, which subtracts however much of this I want. And then there's also going to be a C, I'll call it tilde of mu, such that when this counter term, you get this part here, the mu dependence in this C tilde is designed to exactly cancel the mu dependence that appears in the loops. Because we need a mu independent answer for any observable quantity. Repeat it one more time. Let me repeat it, but with actually writing some equations. Maybe that'll make it help. What can I erase? So I'm going to give you it's not going to be correct yet. It's not going to be the full answer because actually I should have kept that equation. Too late. I'm just talking about a single integral, and I haven't done the full calculation yet, but we can pretend like that was the entire correction to the self-energy. So we have this loop, and I'm saying I have to add a counter term. And the loop, when I include the other factors, gives, let me call it the self-energy. Or no, here we get this amplitude, which is minus the self-energy. And what we found from the loop integral is we get this 2b m hat over 6f squared times this integral we just evaluated. And then what I'm saying is we have to add a counter term. So I'm going to add a new operator into the Lagrangian. So just heuristically, again, this is not correct because we haven't done the full calculation, but I'm going to have some counter term operator that has to scale like some C epsilon plus C tilde mu, and then it's also going to have to scale with 2b m hat over 6f squared. So then, what? Thank you. So the incorrectness is, remember, these aren't the degrees of freedom we're using in the theory. We have the sigma fields. I'm just being, like if you're doing complex scalar field theory, this is what the operator would look like. You'd have your, phi dagger phi. And I have to add, I know it scales like this, and I have this integrand. And so then when I add it together, this C epsilon will come with the opposite sign. So in my notes, I did the self-energy, and here I'm trying to do the amplitude, so I got some minus signs floating around. I think I need a minus sign here, so that when I calculate, so C epsilon will be 1 over epsilon minus gamma plus log 4 pi plus 1. And then it has to multiply m squared over 4 pi squared. Because my loop integral has m squared over 4 pi squared, 1 over epsilon. And so you can see I have a plus from that. And then the C epsilon operator comes with a minus sign, so the 1 over epsilon terms exactly cancel. But then there's this leftover C of mu part, so now I have a C epsilon. And then the C epsilon times 2b. And then I also get, sorry, it's minus because of the minus sign. And so now this will cancel all the divergent parts. So I'm left with 2bm hat over 6f squared. And from here, there's an m squared over 4 pi squared log mu squared over m squared. And this is the same. There's, as I wrote it, there's a minus sign, so then I'll have minus c tilde mu of mu. And the statement is, so first of all, the c tilde better scale like m squared as well, because I have to cancel the log. So the point is, this is minus some self-energy correction. The energy of a particle is an observable quantity. So for all observables, we demand that the partial derivative with respect to the renormalization scale of our observable is equal to 0. There can't be any dependence on the scale mu because it's just some fictitious scale we stuck in the theory to understand what's going on. And so what that means is you can deduce the mu dependence by simply taking the derivative of this internal part with respect to mu and demanding that this has the right mu dependence to cancel against this one. And so you'll get a log mu inside of here as well. Since there's a minus sign here, we can just deduce c tilde of mu must equal m squared over 4 pi squared log mu squared, and then we're stuck picking some other scale, mu naught. So this is part of the renormalization prescription. You have to choose a scale at which to renormalize the theory. That's your choice, mu naught. And typically, you'll set mu naught to something like a cutoff of the theory. So in this particular case, a convenient choice is to set mu naught to 4 pi f pi. Because then you'll see, if I set mu to 4 pi f pi, then I get a m squared with the 4 pi f squared, which is the small expansion parameter of our theory. So that's very convenient. But then that means you set the scale mu naught to 4 pi f pi. But the actual mu dependence exactly cancels in the sum of the terms. So that's critical if your theory is going to make sense. Okay, now why is this logarithmic m squared term interesting? So we just added a new operator to the theory that exactly canceled all this stuff, which I'm saying is all short distance physics we don't care about. You cannot add operators to the theory to cancel this log m squared term, because a log is a non-analytic function, so it doesn't have a convergent Taylor series expansion around the origin. So there's no way, by adding a finite number of powers of m squared operators to your theory, can you cancel the log. So in quantum field theory and effective field theories, which are just quantum field theories, the interesting physics is always contained in the non-analytic functions. That's where the infrared physics is hiding, so to speak. So all the interesting physics is in the infrared, which is the low energy dynamics of the theory, and that's the physics we want to keep track of. Especially when you start comparing to lattice QCD, this log m squared is also the kind of thing, if this is a pion mass, you know, if you only had a polynomial in m pi squared, you could just fit it with a nice polynomial, but if you have logarithmic corrections in there, those will curve faster than a polynomial, and so hopefully they'll be detectable when you look at your lattice QCD results as a function of the pion mass. In the same way, if you encounter, so again, in chiral perturbation theory, I'll just put this over here, remember, from the perspective of our low energy theory, the parameter of interest is our quark mass, right? And so in the low energy effective theory, this is this BMQ term that appears in the Lagrangian. So when you start matching QCD to chiral perturbation theory, the low energy effective theory will have operators that can be expressed with powers of BMQ, integer powers. So we can have BMQ to the n, where n has to be an element of the integers. Positive integers. What's the positive integer? It's z, no, I don't remember. Z plus. Only positive integers. And recall, m pi squared scales like BMQ with the 2, right? If this is the average quark mass. So what that means is if you had a correction that looked like m pi, if you derive some correction that looked like m pi, this is going to scale like the square root of 2b quark mass. The square root is also a non-analytic function. So if you encounter something like this in some calculation you're doing, this is infrared physics. You cannot subtract it with a counter term. Another interesting thing, if you derive some loop correction and you find it scales like m pi, can it have an ultraviolet divergence in dimensional regularization? Can it have any mu dependence? Why not? If I have mu dependence, what do we have to do? We have to have a mu independent answer. How do you make it independent? You have to add a counter term with mu dependence to cancel it. So if you have something that scales like m pi, there cannot be any dependence on a renormalization scale. If you have something that depends in some non-analytic way in the quark mass, there cannot be any scale. So if you find that you have scale dependence, you've done something wrong. Because you cannot add an operator to absorb the scale dependence for something like this. This is a very useful tool when you're doing calculations. Okay, so now we're renormalizing the theory. So now let us come back and actually do the complete calculation with the pion mass terms, which I inconveniently erased. They're all gone. I have to write them again. So we have this self-energy correction so far arising from the mass operator is I 2bm 6f squared, and then we had 1 contribution from the pi 0 and 4 from the charged pion. And at leading order, at this order, m pi 0 is equal to m pi plus. So we can just combine these. And so what do we get? 5 over 6 2bm, and now I'll get rid of the I, get my minus sign. There's this 1 over f squared. And remember, what we have done now with dimensional regularization is the magic of subtracting the 1 over epsilon. We know there's a counter term in the theory. We haven't written it down yet, but we know it exists to remove those divergences. And all we're going to be left with is this logarithmic dependence. And so then I get m pi squared over 4 pi squared log mu squared over m pi squared. Now, it's interesting. You can choose at this order, or in any order, you can choose for m pi to be the bare mass, or you can choose this pion mass to be the physical mass, the on-shell physical mass. That's your choice. whichever choice you make, as you go to higher orders, you will have to make corrections to account to the fact that you made that choice. Remember yesterday we were talking about the scattering amplitude, and I separated the term that was 2b m hat from the term that was from the on-shell momentum. It was m pi squared. And I said if we go to higher order, if we want to work with the physical parameters, we have to turn our 2b m hat into a physical mass. And I can always relate that by taking, 2b m hat is equal to m pi physical squared times 2b m hat over m pi physical squared. And then this, we're working out what the calculation is, but this is going to be some perturbative calculation. And we talked about earlier how epsilon pi is a correction of order 2%. So this is a very good perturbative expansion, and I can just invert the correction and build in the higher order corrections we're working out to correct any instance of the 2b m hat. And usually, in field theory, it's almost always more convenient to use an on-shell renormalization prescription because effective field theories and quantum field theories, they usually converge faster in perturbation theory if you use an on-shell prescription. Ultimately, the answer should not depend if you use the bare parameters or the on-shell parameters, but you might find you don't have to work as hard if you use on-shell because the theory converges faster. Okay. Now, note, okay, let me just rewrite this expression one more time. I have minus 5, 6, or let me write it this way. 2b m hat minus 5 over 6 times, I'm going to take the f in here, and now I'm going to have m pi squared over 4 pi, and now I'll just call this f pi, which is got higher order corrections compared to f. But again, if I do perturbation theory and I change this f into an f pi, that's going to come along with an epsilon pi squared suppression, so that pushes the difference to even higher order. So it pushes it up to n2 I'm free to do that because it's perturbation theory. And so you'll notice when we have a counter, I said we just had a counter term that we added to subtract the 1 over epsilon. Look at this. This is 2b m hat, which is m pi squared, or I could turn this m pi squared into 2b m hat. This scales like the quark mass squared, not like the quark mass. What does that mean? It means our original operator in our theory cannot be the counter term. Why can it not be the counter term? Because if you recall, I said we're matching QCD to chiral perturbation theory with a known source for the quark mass. So the quark mass is a very specific source, and from a theoretical perspective, I'm free to change the value of that source. So if I were to change the quark mass, I could tune this counter term to cancel the 1 over epsilon pole at one particular choice of the quark mass, but then if I change the quark mass, because this goes like mq squared, I would ruin the cancellation as soon as I move that quark mass to a different value. So this renormalization demands that we add a higher order operator to the theory. So that's one of the things that happens in effective field theory. You have to add higher order operators. We expected it anyway, but this tells you if you want to renormalize the theory consistently, you have no choice but to add a higher dimensional operator. Okay. 15 minutes left. Now we're going to do derivatives, because this is where it gets a little more fun. All right. So now let's look at the derivative interactions. Maybe I can remember to leave the Lagrangian. So the second order derivative with 4 pi fields, I'll just write it down from yesterday. We had a few operators. And I guess we have 15 minutes of questions too, so feel free to ask questions in the next 15 minutes, of course, as well. If anything, I should just say, any questions about that before we move to the derivatives? Yeah. I don't quite understand the question. So you're saying,
You can renormalize by using counter terms.
yes.
And you can also renormalize putting some quantity that the variance in a non-observable quantity like the particles. You can do that in this unit.
Is the question, can I modify the quark mass to, so no, because the quark mass is the source for my psi bar psi operator. And that's absolutely fixed if I want to match QCD to chiral perturbation theory. That's me as the theoretical experimenter turning on the quark mass as a source. This is an external parameter I get to control. And that means, okay, I'll repeat myself. So that means because this divergence, so rewriting it in Baire parameters, and I think I lost, no, there's the minus sign. I have 2b m hat. Remember, m hat is the average of the up and the down quark mass. So if we're working the isospin limit to the same, I can just think of the quark mass. And then in here, I get m pi squared is also a quark mass, right? And then I have the 4 pi f squared and the other stuff. And the point is, this loop integral correction came from this Lagrangian with a single insertion of the quark mass. So, in principle, I could come up with some scheme where I absorb the 1 over epsilon that's associated with this correction. So if I didn't take off the 1 over epsilon yet, I'd also have the plus 1 over epsilon divergence. In principle, I could absorb this 1 over epsilon into this operator, but because MQ is this knob I'm allowed to turn, I can only make that cancellation happen in one value of the quark mass, not for any choice of the quark mass I want. And my statement is, because this is the source that I get to control, I have to have a scheme that works for any quark mass I pick. So there's no way I can modify this quark mass to absorb this divergence consistently for any value of the quark mass. Thank you. Yeah.
Is there some specific case when this procedure doesn't work?
The dim reg,
The regularization scheme.
when you've made a mistake. If you have a quantum field theory, this will always work. If you have a perturbative quantum field theory, this will always work. For example, perfect case, you will never see confinement come out of perturbation theory. All the loop graphs you calculate will be perfectly well defined. Like, the regularization will work, but you'll just miss a bunch of physics, non-perturbative physics. So, in perturbation theory, and dim reg is actually the only regularization scheme that works for QCD, perturbative QCD, because in QED, the Ward identity protects you from the orthogonal, what do we call it? You know, the helicities of the photon, you have the plus and the minus, and then the transverse helicity. So when you use Pauli Villar's regularization, the transverse photon component picks up a mass. But the Ward identities of QED protect any physical observable from being sensitive to that transverse component of the photon mass. When you go to QCD, the extended Ward identities, which are BRST symmetries, don't prohibit the orthogonal or the transverse gluon modes from contributing to physical observables, so Pauli Villar's does not work in QCD. So as momentum cutoffs can work, but they have similar problems, but they also break chiral symmetry. And so if you are doing calculations with quark masses, even if you set the quark mass to 0, if you don't use a regulator that respects chiral symmetry, you'll introduce a bunch of chiral symmetry breaking physics, which will blow up all your integrals, and you have to finely tune and cancel them. So dim reg is the regularization scheme of choice for a non-abelian gauge theory. And it will always work in perturbation theory. Once you go beyond 2 loops, it gets much more complicated. I think through 2 loops, you can have perfectly mu independent quantities you compute, you can exactly cancel. But if I'm remembering correctly, beyond 2 loops, you get some residual mu dependence you can't perfectly cancel at a given order in perturbation theory. It's like, don't quote me on that. Some problems happen, some difficulties happen beyond 2 loops. Okay. Other questions? I'll keep writing, but if there's more questions, please speak up. I'm going to write down one operator we don't need. So the first 3 we're going to need, and this last one we're not going to need. So this is from the kinetic Lagrangian. There's 1, 2, 3 more operators I haven't written down. These are the only ones that are going to contribute to the self-energy, and let me show you why. First of all, of course, we must have at least 1 pi plus and 1 pi minus, because this has to have a derivative here. We're renormalizing the self-energy of the pi plus. You can have 2 pi zeros, that's fine. Yeah, okay, everything's good. Now this operator, where I have 2 derivatives on the pi plus field and nothing on the pi minus, this will generate a correction for you that scales like this, where I have, let me use a dot to denote there's a derivative. So I have a dot on an external leg and a derivative on an internal leg. And so what is this going to do? This is equal to 0 by Lorentz symmetry. So how do we see that? This is going to give an integral that looks like, I don't need to write that. This will give a correction. Look, it will depend on the external momentum of my pion. And then I'll have an integral and if that's not obvious to you why that's 0, again, k is a fictitious dummy variable. The only way this integral could not vanish is if there was dependence in the integrand on some external physical parameter that's not a dummy variable that also has a direction. So because there's nothing else other than this scalar m squared in here, this integral has to vanish. Right? It's just 0. And here, I don't have to do anything tricky. I just have an odd integrand and an even, I have an odd function and an even integrand. And so it just vanishes automatically. Let's leave this here and do the other kinetic correction over here. So we're not going to complete the calculation given the time, but we're going to get pretty close. So what do we have? If we look at these other 3 operators, how are they going to contribute? Again, they're going to contribute to graphs where I have 2 derivatives on the outside, or I can have 2 derivatives on the inside. So sometimes the internal propagating particle is a pi 0, so I can have a pi 0 with no derivatives, a pi 0 with 2 derivatives, and then this middle operator where I have a derivative on the pi plus and the pi minus. When I do the Wick contractions, I'm going to have the choice. Do I send those derivatives to the external state or to the internal state? So what do we get? The self-energy correction from all of this is going to be again, I'm using dimensional regularization. And then what you can show is you're going to get a p squared. Again, if it's external, one of the momentum is coming in and one's coming out. So I get a minus IP and a plus IP, so the I is canceling. I get a p squared, and I have a propagator of the pi 0. If it's the derivatives of the pion inside the loop, I get again a pi 0 propagator, but now with an internal loop momentum. And then with the middle operator, I can get the momentum goes inside or outside. And these propagators, again, the pions are the same, so these are just I over k squared minus m squared. So what do we get? If we add it all together, we can see these two terms are the same. They both just have a p squared plus k squared, and since the pi mass is the same, I can set the propagators to be the same, so I get a factor of 2. An overall factor of I from the propagator. Now the p squared, it's easy, I just pull it out. That's the integral we just did for the quark mass term, except now I have a p squared, which is my external momentum, which is just m pi squared. Now this is a physical pion mass. So if you wanted to turn this into the bare pion mass 2b m hat, then you'd have to add your corrections to change it from the physical on-shell mass to 2b m hat. But we're going to do the on-shell scheme, so this is just m pi squared. That's easy. What about this other integral? So this is a fun one. So I have k squared over k squared minus m squared. And of course, how do we do this? We add 0. So we do minus m squared plus m squared. And so then, what do we have? This one's easy again. Same thing, we already did that. What is this integral? Why is it 0? Yeah. This is a fun dimensional regularization. Because there's no physical scale for this integral to depend on. It can only be some uninteresting ultraviolet physics. It's 0. Okay. Now, since there's a couple minutes of questions, I can go just a tiny little bit farther. Yeah, I will try to finish up. So when we add the momentum, we've already done all the integrals. I just have to keep track of the algebra. What are we going to get? Let me come back over and add it to my quark mass term. So now my self-energy from the kinetic operator is going to be I get 1 power of the pi mass, and then I have a p squared plus m pi squared. Now I haven't set it to the mass yet, because what we want to do is use this to get at what's called wave function renormalization. It's the last thing I want to tell you before stopping. And this is times log. Here okay. Minus, so I can keep the mu squared over m pi squared the same. I usually write the m pi squared on top, but that's a negative, because I always set mu to a large scale, so then it's negative, so this way it's positive, but then, all right. So this is a self-energy correction from the kinetic operator, and it has this p squared term in it. Now, what we'd use the p-squared terms to do is figure out what's called the wave function renormalization. If you recall, the full propagator is going to be given by something called the wave function over p squared minus m squared minus some self-energy. And the propagators we've been using so far have z equals 1. Now, the problem is when you do the LSZ reduction, which we have been implicitly doing without talking about it, and you amputate the external leg, you have to amputate the fully dressed on-shell external particle, which means I need to worry about the fact that z is not exactly equal to 1. So we need to figure out what the corrections from our 1 are so that we can appropriately dress our external lines to remove those corrections when we do the LSZ reduction and amputate the external legs. And the wave function renormalization is simply given by, for a boson, the derivative, sorry, it's getting ahead of myself. The wave function renormalization, I call it delta z, is given by the derivative of the self-energy correction with respect to p squared. If this were a nucleon or a fermion, I would have to differentiate with respect to the linear momentum, not p squared. But it's a boson, so I differentiate with respect to p squared. And so here, what do we get? This minus sign and this minus sign cancel, and I must be missing a factor of I. So this is my wave function renormalization, the derivative of the self-energy with respect to the external momentum p squared. I'm going to hold this here for a second because when you actually want to evaluate the shift in the pole mass, I don't have to worry about the z factor, the wave function renormalization. I can simply just set p squared equals to m squared to get the shift in the mass. And so then if I put it all together, this correction to the pion mass through the loop order, in an on-shell scheme, I get this small parameter suppression I'm expecting, and then a log mu squared over m pi squared, and then 4/3 p squared minus 1/3 m pi squared. So then when I set p to its on-shell momentum, I just get m pi squared. So then I get minus m pi squared times, I'll just now call this epsilon pi squared. And then if I set mu equal to epsilon pi squared, or so if I set mu, let me just write it. And then let me pick mu is 4 pi f pi, and this will equal now plus m pi squared epsilon pi squared log epsilon pi squared. So there's the self-energy correction of the pion. We still need the counter term because we haven't absorbed the mu dependence. I won't talk about the counter terms. In the exam, the operators will be written down for you. And so those counter terms, you don't have to do much with them. But what you can work out later after the school is see how you have to modify those counter terms. What mu dependence do you need to add in order to exactly cancel the mu dependence you see in the self-energy correction? So if you feel like taking this a step further on the plane ride home, you can put yourself to sleep by trying to work it out. And then the last thing I'll say about the wave function renormalization, say we were calculating corrections to this quantity f pi. Remember, we talked about that before, where I have a pion come in, it hits the axial current and goes into the vacuum. So if I wanted to calculate loop corrections to f pi, I would need to add terms from the Lagrangian that have 3 pion legs and look like this. And then there's going to be some counter term for f pi, which I'll draw with some other symbol. And then the other thing you have to do is you have to add the leading order correction times 1/2 the wave function correction. So the algorithm is just talking about one loop order. To go beyond one loop, you have to be a little more careful. But at one loop, you compute loop graphs. You compute the CT for counter term at one higher order. And then you have to add the I'll call it delta z, 1/2 wave function times leading order times the number of external legs. So if you have f pi, there's only one external leg. Oh, you can have, from the counter term, Lagrangian, you can also get shifts in your wave function. So you have to be careful with that. So the counter term Lagrangian will also have things that add to your wave function or normalization that you have to multiply by your leading order amplitude. So this is essentially the algorithm to go from tree level to one loop. Is it the complete? I think this is the complete algorithm. And again, the power counting. If I go to one loop with the leading order Lagrangian, I need tree level with next to leading order. If I go to two loops with the leading order Lagrangian, I will need one loop from NLO Lagrangian and tree level from N2LO. And that's all comes out of the power counting. So once you figure out, like we're talking about the integrals, how to scale, how they scale with the power counting of the theory, you just count what that is. And then you go to next to leading order and say, oh, I need to add a loop in order to get to the same power counting. And then at N2LO, oh, I only need tree level to get to this power counting. So if you work to epsilon pi to the n, this is what dictates for you exactly how high in order you have to go from any Lagrangian. And it always follows the pattern. The lowest order Lagrangian has n loops. The next to leading order Lagrangian has n-1, and so on, until you start doing baryons, and then it gets all confusing. But the power counting still holds. You just figure out what order you're working to, and you can figure out every graph that contributes to that order. And again, remember, all the interesting physics is in the non-analytic structure. The log m pi squared, square root m pi, or square root m pi, or m pi effects, which is square root mq, that's where all the interesting, and it's not just an effective field theory, that's a statement about all quantum field theory. The interesting infrared physics always comes in non-analytic dependence on your small parameters. Okay.
All right, let's thank André. Do we have some questions? More than what we had before? Yeah, okay.
How to extend the effective field theory to a non-perturbative approach?
Well, the effective field theory is constructed as a perturbation theory.
Okay.
So the non-perturbative physics is encoded in the values of, remember this B parameter, that encodes the non-perturbative physics. And so you get at the non-perturbative physics by matching, in this case, your effective field theory to either lattice QCD or to experimental data. If you have experimental data, then you can't change the quark mass, so it becomes more tricky to determine. So when you go to the next order, as you'll see in the exam, there's 4 operators at NLO. So then you have to determine 4 new coefficients. And so how do you do that? So it gets trickier and trickier to determine them from experimental data, whereas lattice QCD can give you an orthogonal approach to get access to some of them. I think the one case I'd say where you might get at non-perturbative physics with your effective field theory, it gets into territory that is debatable whether it is really in the regime of the effective field theory. But let me consider pi-pi scattering in the rho channel. So if you use effective field theory to calculate pi-pi scattering in the rho channel, you'll have some graphs that look like this. What is the row channel? Okay. Row is, this is isospin 1. It's going to be L equals 1, so meaning it's an odd partial wave. So if you look at, say, pi plus pi 0 scattering in the isospin 1 channel, you will find there's a resonance, if I can remember how it looks. I don't remember the cross section, but the phase shift will come off slow and then we'll have a steep rise around 770 MeV. So here's the center of mass energy, the Mandelstam S of my pi system, and there'll be this rise where it approaches 180 degrees. So it's the hallmark of a resonance. And the rho is well described by Breit-Wigner, unlike most resonances. So the issue is, if you want to describe this system with chiral perturbation theory, if you just compute all these graphs, your scattering amplitude will never generate an imaginary piece of the mass position. And so, in fact, chiral perturbation theory doesn't satisfy unitarity unless you do something called what's called unitarized chiral perturbation theory, where you basically take these S-channel graphs and you sum the entire series of them non-perturbatively. And so then, just like the geometric series, what you'll do is you'll resum some physics back down into the denominator. And what you find in chiral perturbation theory is in order to satisfy unitarity, you need, if I work to one loop, you need next to leading order loop graphs to cancel against a tree graph in order to give you the resonant physics. And so now you have competition between next to leading order and leading order just to see the position of the roll. And that's where it's debatable if this is really in the regime of the effective field theory or not. However, it works remarkably well. So oftentimes effective field theories, they have a breakdown scale, but they tend to work well beyond where they're supposed to stop working. And if you get a little more clever, I think if I talk to Jose Pelez in Madrid, is that where he is? He will tell you what you're really doing is you're not asking NLO chi-PT to compete against leading order chiral perturbation theory to satisfy you. So how does that mean? Remember, optical theorem tells you this squared is equal to twice the imaginary part of this kind of physics, right? Twice the imaginary part means I do a cut. He says, you're not really asking chiral perturbation theory to do this. What you're doing is you're going to use dispersion theory and figure out some subtraction constants you need to do. And you're going to do your chiral perturbation theory on those subtraction constants, which is well defined. So he has, I think, a more rigorous approach to it. But I'm not an expert in this. This is just an example of where people try to build in non-perturbative physics with the effective field theory. Many other effective field theories as well.
Thanks.
Any more questions?
We all need coffee, don't we? Or at least to stretch our legs.
All right. So let's thank André again. Thank you very much. Now coffee break.